Thank you, Clyde, and good evening, ladies and gentlemen. I don't know the backgrounds of anybody here except for Clyde, and so I'm not assuming any amount of geology background or science background. So when I give the talk, I'll be explaining things that may be obvious to some of you, but just make sure that everybody knows what I'm talking about. I suspect most of you have heard of the Ring of Fire, which is the ring of active volcanoes that encircles the Pacific Ocean. And so that's what I'm going to be talking about. Antarctica fills in the gap, but the volcanoes in Antarctica are different from the ones elsewhere in the Ring of Fire. The couple different things that I'll talk about: they are less explosive. They are actually bigger than most of the ones in the Ring of Fire. I'll show you some pictures of some that are as much as 2 to 3 times larger than Mount Shasta, which is the largest volcano in the Cascades. And that's just for the part that's exposed above the ice sheet. Most of the ones that I'll be showing you are like islands in the ice sheet with an unknown amount of the volcano below the ice. And so when I'm talking to you about volumes of them, it's what we can measure, which is what's exposed. They also have a different shape and a different composition than those elsewhere in the circum-Pacific belt, and I have a few rock samples to pass around at the appropriate time to give you an idea what these look like. One of the interesting characteristics of them is in the Antarctic environment, most of them are not dissected by erosion. That is, they don't have valleys or cirques cut into them because the ice sheet, a cold polar ice sheet, is not very effective at eroding. I'll show you examples of that. But anyway, I'm going to describe the differences and explain them as I go along here. So this is just a rough outline of the sequence that I'm going to describe things through. I'll talk to you first an introduction to Antarctica, and then an introduction to the ice sheet, and what influences the Antarctic environment have on volcano characteristics, transport and accommodation in Antarctic field camps, and then the Ring of Fire, what is different about the Antarctic sector. And then how do you work in a penguin rookery? I'm talking about hazards, I'm kind of joking here. And then a lot of the slides are metric, some of them are in feet and miles. So so you may know this already. A meter is 3.3 feet, or just a little over a yard. 3,000 meters is 10,000 feet. 8 kilometers, 5 miles. I'll try to do some of the conversion for you as we go along. So this is a map of Antarctica. I put another one, whoops, I keep pushing the wrong button here. I've got a map over here, I'll refer to that periodically. But the convention is that for maps this size or this scale, the Greenwich meridian is always up. And so Chile is up here. We are 16,000 kilometers or 10,000 miles straight north of the area that I'm going to be describing mainly. These are the volcanoes that I work on. And so most of the slides that I'll show you are from here, but some of them are from over in here, and some are from up in here. And I'll try to remember to, that's why I've posted this over here so I can point out just where the slides are. It's roughly circular, the continent, and it's about 3,000 miles across in almost any direction. So that's essentially the distance from San Francisco to New York City. So if you put Antarctica over the United States, it would extend well up into Canada. So it's really, and then the other, this part is East Antarctica, so called because it's almost entirely in the eastern hemisphere. And it is mostly above sea level if you remove the ice sheet. And it's also very stable geologically. We call it a craton, which is a geologic term for a stable continental block. Stable meaning no earthquakes, no volcanic eruptions, very little uplift or subsidence, no mountain building and that sort of thing. So this is the craton. I'm not going to really talk about this at all. Did I get, oh yeah, there we are. Okay, so this part is West Antarctica, all of this lying entirely in the Western Hemisphere. And it is geologically active. It is what's called a rift system, where the crust is being stretched and thinned, and there is faulting and volcanic activity. So in other words, it's ruptured, and I'll show you a cross-section that I hope will give you an idea of that. So this is West Antarctica as it would look if the ice sheet were removed. When you remove ice, you get what's called glacial rebound. That's what's happened all over the northern part of the United States and Canada as a result of the melting of the Pleistocene ice sheet. You get enough uplift so that the ports on the north side of the Great Lakes in Canada are shallower than the ones on the United States side. So this is what it would look like then after the ice sheet was removed and you got this rebound. And what you can see here is that most of West Antarctica is below sea level. The parts above sea level are in red and brown. The yellow is from sea level down to 5,000 meters below sea level. The green is minus 5,000 to minus 1,500 meters below sea level. And these little blue troughs in here are below 1,500 meters below sea level. One of them is as much as 2,500 meters below sea level. So the parts that would be above sea level are this area, which is where I work, a little bit of it here as well. So this is the West Antarctic rift system where the extension, faulting, volcanism are taking place. And so most of the volcanoes, this is the rim of fire, essentially. And I'll show you more of it later. But most of the volcanoes then are along the coast, along in here. The ones, there we go. Over here, that one that I'm pointing to is Mount Erebus, which is the most familiar one in Antarctica. I'll show you a picture of it later. Here's another active one. The open circles are the ones that are active. And so there are some here, 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 and here. These have not been observed to be active. I mean, nobody's there. And so if one erupts, the only way you would know about it is if a satellite happened to be passing over it. But there are deposits that are young enough that we can infer that they're active. So these volcanoes have been active from 25 million years ago to the present, and these over here from about 45 million years ago to the present. So most of these start below sea level or below ice level, like this one. So, and I'm going to show you a picture of this. This was the volcano that you saw in the first slide, and I'll be showing that to you again. And it started 3,000 meters, started eruption 3,000 meters below sea level, and has built itself up to where it's about 12,000 feet above sea level. And that's where it's located, right in here, 10,000 miles straight south of us. And then This cross section is a sort of a schematic diagram to show you what the geologic structure would look like. It's like if you cut a trough along here, okay, you would see faults like this. And the thing to notice about these faults is, see, there's a fault here, another one here. For this block to go down, you have to pull this apart because this is inclined this way and this one's inclined this way. So these are the kind of faults that form when you are actually extending the crust, which is what's happening all across here. As I say, I'll show you a picture of that one a little bit later. So most of these volcanoes are like islands above the ice sheet. The closest analogy that I can think of when people ask me what does it look like down there, if you've ever flown into Seattle when there's heavy cloud cover and you see Rainier and other volcanoes sticking up above the cloud cover, that's what it looks like along here. But if you're in here, it would just be dead flat and white with blue sky. Anyway, the ice sheet its maximum is about 4 kilometers or 2.5 miles thick, which is right in here, starting well below sea level and going up to an elevation about 8,000 feet above sea level. Average elevation of the whole continent is about 8,000 feet or 2,400 meters, and that's because the ice sheet has roughly an average thickness of 2 miles. So you're really looking at the top of this very thick ice sheet. Those of you that can see, it's a National Geographic diagram, the black letters are the surface elevation, and the blue ones, which you probably can't read, are ice thicknesses. And so there is the one that's where the ice is 4 kilometers thick. Right here, it's 3 kilometers or 10,000 feet thick. And if it all melted, the whole thing would raise sea level about 60 meters, over 200 feet. But the part that is most unstable because it's grounded below sea level is the West Antarctic ice sheet. This is the one that people worry about. If that all melted, sea level would rise 3.3 meters, around 10 feet or so. And that's because it is grounded, meaning it rests on bedrock below sea level. So all this light brown is below sea level, like the diagram that I showed you earlier. And if it melts enough so that it no longer rests on the bedrock floor of the continent here, then it would start to float, and then it would deglaciate very quickly, and that's what people worry about. And it has actually, this area right in here is the area that people are monitoring very carefully, because the outlet glaciers in here are moving very rapidly and they are melting very rapidly. And so the concern is that this will sort of flow out and melt fast enough that it will cause the rest of the ice sheet to rise off the bed of the glacier and cause very rapid deglaciation. So the ice sheet is a huge glacier, and glaciers are formed essentially by compaction of snow, compaction and recrystallization. If you drill down through the ice, you go from snow at the surface to firn, which is like corn snow, and then into what is called bubbly ice. That is ice with lots of bubbles of air, and then as you go deeper and deeper and the pressure increases, the air gets squeezed out and you get fewer and fewer bubbles until you finally get blue ice. And for those that core the ice sheet, it's always fun for them to take samples from the core and put them in their drinks, and then watch when the ice melts and the bubbles explode because they're under a lot of pressure. So this is a volcano core, a small one. This is a mile across. So that's the direction of ice flow. And these are crevasses. The dark is where you have snow bridges over crevasses. And you can see from the scale that these are really big. The upper part of a glacier is brittle, and the lower part flows like hot tar or honey. And so as it moves around an obstruction like this, the brittle upper part fractures and forms these big crevasses. So these are unusually large. You obviously don't want to be anywhere around that. If this breaks, if you were to like go across it in a snowmobile and it broke, it would be like falling off a really high cliff down into the crevasse. Oh, and this is right on the coast. The Amundsen Sea is out here. And this volcano is being eroded and transported to the sea by glacial erosion. There we go. Okay, I've got a few more pictures to show you what the ice sheet looks like. I mean, it flows, but it breaks up into streams that flow down to the sea. And so what you see here is a glacier flowing down here. This is the sea down here. And this is freshwater ice, the glacial ice, so it floats high in the sea. And then this is frozen seawater, and so it doesn't rise nearly as high as the glacial ice does. And that is not a ladybug, it's a helicopter for scale. So this is a small glacier, and it is located way over here, right at the sort of northwest corner of the Ross Sea, right in here, and about 72 degrees south, and it empties into the sea, as you can see. But if you go further north, the ocean gradually gets warmer as you get further and further north. And if you get up to the tip of the peninsula where most tourist ships go, it's warm enough that the glaciers get trimmed off right at sea level. That is, they flow out into the sea and they melt before they flow out, and as this does, or like this one. This is located down in here. And so what you're seeing is an ice shelf where the glacier has flowed out and is floating. So this is the mother of tabular icebergs. That is, when this breaks off, you get bergs that are flat-topped. And this is sea ice, which is just frozen seawater. And so this, it isn't like I've gone and measured this, but it's we've seen these from icebreakers that I've been on, and this is probably about 200 feet and extends probably 800 feet below sea level. About 1/5 is the tip of the iceberg, so to speak. So this is an old berg. As these bergs flow into the sea, they melt and deposit sediment, which are these dark bands in here, like this. And you can see from the top here that it was a tabular berg, like that. And then this is sea ice. Where do I have to? Oh. Okay. These are emperor penguins. They're about 3 feet tall. So this stands only a few feet above sea level, maybe 6 feet at the most. And this is what, when you're in an icebreaker, this is the ice that the icebreakers break. And the way they break it is the icebreakers have a round keel, and they ride up on the ice, and the weight of the ship breaks the ice, and that's how they progress. You go about 6 knots when you're breaking ice. In the open sea, you get a pretty rough ride because there's no keel. I mean, it's a round keel. So I've been on breakers when you're in the Southern Ocean where you get heavy seas. You get as much as a 50-degree roll, 50 degrees this way. It's uncomfortable.
All the scientists constantly sick.
Pardon me?
All the scientists constantly sick. That's terrible.
There are some that don't get seasick. I tend to get pretty seasick. And the only thing that helped me out was a scopolamine patch. And they gave me every kind of pill you can imagine. None of them worked. And then they put a scopolamine patch behind my ear. And within an hour, I felt fine. Went up to the galley and had lunch. And so, you can. And with the first icebreaker I was on was 300 feet long, and it just rolled. And then I was on another cruise on a 400-foot one, and that one rolled and pitched. So you got this kind of corkscrew motion. Even with scopolamine, I was feeling a little bit uncomfortable. So what else do I have on here? So yeah, I told you these are about 3 feet tall. You'll see more emperor penguins further along. Okay, this is back to this volcano that I was pointing out called Tony Mountain that started 3,000 meters below sea level and then has built itself up above the ice sheet. So it is located right in here. And so the summit of it is 95 meters, which is about 12,000 feet. The ice surface elevation here is 1,200 meters, which is about our elevation here in Denver. The base of the volcano, as I've told you, is 300 meters below sea level, and the thickness of the ice is about 2,000 meters. And that summit is about 60 miles away from here. So that's fairly typical of what the volcanoes here look like. That is, they are islands in the continental ice sheet. So this one in the next 10 slides shows some effects of the Antarctic environment. And this one is relatively unusual. This just gives you some dimensions, but most of the volcanoes that I'm going to show you show little or no erosion. This one is an exception, has a great big cirque here, and that's because it lies on the coast. The Amundsen Sea is right out here, and the greater warmth there yields more meltwater, and the meltwater that freezes and thaws is what helps the glacier to erode. That is, the meltwater seeps down into cracks in the rock, then freezes. The glacier moves and plucks out these rocks, and that's what causes the erosion. And now, this is an air photograph taken by the Navy from a plane, and the next picture is one that I took from here, just to show you what it looks like on the ground. Now, for the photographers here, these were Kodachrome slides that I digitized, and you're going to see one of the problems that you have when you digitize a Kodachrome slide. If you this is really not blue snow, but if I made this snow as white as it really is, it would wash out the sky. So you're always trying to balance. I mean, in Antarctica especially, you've got brilliantly white snow and a brilliant blue sky, and you're trying to balance that. And there'll be one slide here where I gave up and I just show it in grayscale because I couldn't get a decent balance in the colors. But anyway, this is about a 2,000 meters of relief like this. The head wall of the cirque here. Now this one is more typical. This volcano is about 5 million years old, the age of the island of Kauai in the Hawaiian Islands, and it shows no evidence of erosion. It doesn't have any cirques, doesn't have any valleys cut into it, and it's about 5 million years old. So as you go, probably a lot of you know this, as you go further northwest along the Hawaiian chain, the islands are increasingly dissected. That is, you get more and deeper valleys, so that you get a really, this is the age of Kauai, and those of you that have been to Kauai know that you get big, deep valleys, a lot of erosion there. And so one of the, so you need water for the glacier to be an effective agent of erosion, and without it, the ice, polar ice, in contrast to glaciers that are in temperate regions, it has a temperature that's well below the freezing point. So it just flows like tar or molasses. There was something else I was going to tell you and I've forgotten what it was. This is Mount Sidley, the highest volcano in Antarctica, and it is located right around there. It's inland quite a ways. And the bowl here was not produced by glacial erosion. It was produced by a major volcanic eruption. And this guy is standing on ash beds produced by the explosion. This is about 8 kilometers across or 5 miles across. One of the things about showing pictures of these volcanoes, there's nothing for scale. So, I mean, I will tell you wherever I can or show you with diagrams what the scale is, because I remember the first year I went down, I wrote a letter to my wife and I told her I'd been on this volcano and the caldera. I said it looked like it was, you know, several hundred feet across. And I went back after I sent off the letter, I measured it on the map and it was 5 miles across. I mean, there's nothing to estimate scale. No, obviously no houses. So this is this is called Mount Berlin. It's an active volcano located right in here. And I want to show you these ice towers, but just give you an idea of the size of this volcano first. And then this doesn't like advancing here. Wait a minute. There we go. That's a caldera. Caldera is a Spanish word. It means kettle. And it is larger than vent. The vent where the lava is extruded from is much smaller. The caldera is a flat, usually circular summit to a volcano, and it forms either from an explosive eruption that blows away the upper part of the volcano, or where the volcano was less explosive. After the eruption is over, the lava is withdrawn and the summit collapses. And that's the way the calderas in Hawaii form, and same here. These form in a similar way. They're not explosive enough, for the most part, to actually blow the summit away. So what I want to show you next are these ice towers, which are, you know, the things that you only find in a polar environment. And you may, if you've been to any volcanic districts like Yellowstone or Iceland or New Zealand, you see what are called fumaroles, where you see gas being emitted from the ground. And in Antarctica, the steam condenses and freezes and forms these chimneys that are called fumarolic ice towers. I've talked to guys that have put an egg, wrapped it in some sort of a pouch and dropped it down and let it cook in the ice tower and pulled it out. I mean, just for the fun of it. So this is an active volcano located right in here. And this one is called Mount Takahe. Takahe is a flightless bird in New Zealand, and so the name was sort of laughingly attached to this volcano because the first field party here was resupplied by an airplane that was not very airworthy, and so they like to refer to that plane as a Takahe, and they attached the name to this volcano. And this one is about twice the volume of Mount Shasta, but it's just the upper part of the volcano. So it's about 20 miles across here. Sorry, this thing, there we go. And then it has an 8-kilometer diameter caldera at the summit, and it has this peculiar feature that we call the mushroom, because we really couldn't figure out what caused it. I'll show, that'll be the first thing I show you, and the second I'll show you these hydrovolcanic deltas, which are produced by lava flowing down the volcano, and then it meets the ice sheet, and it is immediately chilled and then fragmented because you get an explosive interaction between the lava and the ice. The lava has a temperature of around 800 degrees centigrade, and of course the boiling temperature of the water is 100. So it shatters, and I'll show you an example of the rock in a couple of minutes, but the one I'm going to show you is this one. So I'll be showing you a picture on the far side of this, and I'll be showing you a camp scene from here. There's the mushroom, and this is the one that I show in grayscale because my Kodachrome slide would show this either, if I show the snow white, the sky would be pretty nearly white also. And if I show the sky blue, then the snow is all blue. And this shows up a lot better just in grayscale. The moat around here is about 5 to 6 feet deep. So we went down here, chopped away at it with ice axes. We're trying to figure out whether it had a rocky core or whether it was something like one of those fumarolic ice towers that was dormant because we don't see any steam coming out of it. Never could figure out what it was. So we just end up calling it the mushroom. And you can, it's persistent. You see it on air photos that were taken back in the 50s. And I took this picture in about 83, I think, something like that. So it's kind of like a permanent feature sitting in the middle of the caldera at the top of this volcano. So this is the delta. Lava flowed down the slope here and came in contact with the ice, right where you see this boundary. And so it's about 22,000 years old. And as soon as it meets the ice, it freezes and breaks into small glass chips. That is, it's like obsidian. It is obsidian. And then you get an explosive interaction with the melted glacier, and it produces a rock that looks like this. In the dark, you won't be, I mean, you can still see that this rock is made of fragments. So it breaks, the larger pieces are not all glass. The smaller pieces are glass. It's yellow, the sample is yellow because the glass reacts with the water, which is very hot, and it converts the glass to a mineraloid called palagonite, which is a mixture of clay minerals and zeolites. So this is, and it's called hyaloclastite, meaning broken glass, the clast broken hyaloglass. Pardon?
I think there's a fly in Europe.
I just screamed.
So what this is telling us here is that the ice sheet was about 400 meters higher when this delta formed, because all the way up here this was meeting the ice and forming hyaloclastite. So the ice has subsided within the past 22,000 years. And the next picture is going to be just to the right of this. And there's a guy down here for scale. But one of the things you might notice here is you can't follow any of these beds very far before they're terminated. So it's really kind of a jumble. And what you have to imagine is that as this was forming, this is water saturated, basically mud, with a lot of fragments in it. And so it's continually landsliding, and you're getting just turbulent flow of mud and solid slabs like this thing up here. So it's a very active and turbulent kind of deposit. So yeah, this is, when you're working in Antarctica, it's 24 hours of daylight, but the sun is highest in the north, which is noon, and then throughout the day it sinks down in the west, and instead of sinking below the horizon, it just settles and goes along the horizon and then comes back up. So at midnight, it's farthest south, and it's warmest when it's in the north, and the light is best then. So you get better illumination, and it's warmer. You try to work during the warm part of the 24-hour cycle. So this is a closer view of the tuff, and so that's a lava globule that didn't get completely fragmented. And this is like the sample I'm passing around to you, where you've got fragments that are included in a matrix of very fine-grained glass that's been altered to this yellow palagonite. So the only use for hyaloclastites is to build penguin nests. This guy is bringing a pebble over to his mate, who is sitting on the nest here. And this one was taken in late November. A little further along, I'll show you a picture in late January, at which time the eggs have hatched. And so this is taken right around in here on an island right in there. Another place where hyaloclastites have been used is for the Easter Island statues. These are all carved from the same kind of stuff that I'm passing around to you. And this is the largest one. This was being formed when their society kind of broke down and they quit building these statues. And this is the so-called warehouse. These are about half buried in talus, and you can see some that are still in the process of being carved. This is a tuff cone, back here made up entirely of hyaloclastite that probably formed when the lava encountered groundwater, but it's also right next to the coast, so it's probably a mixture of groundwater and seawater. So this is about transportation in Antarctica. This is how we get to Marie Byrd Land. It's a 1,000-mile flight from McMurdo Station, which is located over here, to out here in Marie Byrd Land, which is where we are here. And these are equipped with skis and also JATO bottles. JATO is jet assisted takeoff. And there are racks for 4 of them on either side. And the way they land, they do open field landings with these skis, but then they need to have a pretty smooth surface to get enough velocity to take off. So they, if it hasn't been smoothed out beforehand, they'll go back and forth for a half hour or more to smooth out the surface. Then they go along to take off. They go as fast as they can, and when they've gotten to the maximum speed on the ground, they set off these JATO bottles. So you're sitting in the plane and you hear this hiss. That's when they've set off the JATO bottles, and then the nose lifts and you heave a sigh of relief and you're in the air. So this is camp. This is the bluff that I showed you. This is the hydrovolcanic delta, but we're on the other side of it. This is about 1 a.m. and we've just gotten back and have had dinner. And you know, if you are, what this allows you to do is, like, we were working on the top of the mountain, and it takes a long time to get up there and a long time to get back. So you try to do as much as you can before you come back, so you don't have to keep going back up there. So that's why we ended up getting back this late. And this is, yes, yeah.
What time zone were you using?
Yeah. Okay, what we do, we figure out, you know, how far you are from McMurdo, and we ended up being in the same time zone as we are here, because we're 10,000 miles straight south. But, you know, the time zones change pretty quickly. You know, like when I was on a icebreaker cruise where you're going along the coast, and you had to set the clock ahead every day, even though you're only going 6 knots. So it's almost like getting jet lag on a thing that's going 6 miles an hour. So here we are. This is another snowmobile here. And the flags mark the route in case the weather deteriorates. Well, the kind of deterioration you're probably thinking about is a blizzard, which would be bad. But another one that is less well known to people who don't know the Antarctic is a whiteout. And a whiteout is not a blizzard in Antarctica. A whiteout is when you get complete cloud cover, and when you get that, you can't even see your footprints on the snow, and you would not be able to see these tracks. So a whiteout, you can't do anything except you can go play volleyball. If you're in camp, you can't fly, you can't, because it's too dangerous to try and travel. You wouldn't be able to see crevasses and so on. So this is Mount Erebus here, which is located way over in here by McMurdo Station. And this is a C-121 Constellation, a prop plane. This was taken in 1968. And I flew all the way back from Antarctica to Andrews Air Force Base in Washington, D.C. in one of these. It was the longest flight I've ever had. They stop in Christchurch, New Zealand, then again in Samoa, and then in Hawaii, and then in San Francisco, and then but anyway, it was not too bad. This is Mount Erebus again here, and this is Scott's hut from the Terra Nova expedition. That's the one where he and his party died on the way back from the South Pole. You can actually go in here and look around, see all their provisions and some of their gear. They did find a 100-year-old whiskey cask after we'd been there, so we missed it. And this is Deception Island, which is located way up here. It's called Deception Island because it is the caldera of an active volcano, and there is only one narrow passage to get into it, located way over here. So you wouldn't know this was here until you got in here. And this is about 8 kilometers across, and it has been active. I don't know whether, I don't think it's been active since about 1980 or so. There's a British base down there, and it looks, again, this is digitized from a Kodachrome slide, so it looks peculiar. But this is snow here, and the base was destroyed by a 1969 eruption. Okay, I want to tell you a little bit about why the volcanoes in the Ring of Fire are different from those elsewhere, and how they differ. So they have gentle slopes. They're shield volcanoes like the ones in Hawaii, but they're mainly, well, they really are 90% basalt, but most of that is buried under the ice sheet. So the ones I've shown you before are mainly lava flows. Mount Rainier is mainly ash, and the ash is produced by explosive activity. Kenyte and trachyte are major rock types. This one is kenyte. The trachyte is like granite, except not as much silica, so it has no quartz, whereas the lavas from Mount Rainier or St. Helens would be quartz-rich if they crystallized completely. And this one, maybe you can see this, but kenyte is a variety of trachyte with large almond-shaped crystals of feldspar, named after the main rock type in Mount Kenya. You can, on the flat surface here, you can see these almond-shaped crystals of feldspar. It's a sodium, potassium, aluminum silicate mineral. So this is to show you the shape compared to others. This is a 10 to 12 degree slope, so it's really, you know, a fairly flat shield volcano. The ones in Hawaii have even gentler slopes because basalt is more fluid than the trachyte lava that forms most of this part of the volcano. And this is looking at Mount Takahe from a distance of about 50 miles. You can see how flat it looks. This again is taken at around 1 o'clock in the morning. But it was a 50-mile trip from Mount Takahe to the next volcano. Again, it was not really blue snow. It was white snow, just like all the snow you've ever seen. So compare this volcano with Fuji, which has, well, 30 degrees, probably even more than 30-degree slopes, because it's formed mostly of ash, whereas the Mount Takahe is mainly lava. And this is the Ring of Fire, all except the Antarctic part. And they're formed mainly in a subduction environment, which I will describe in a minute. These triangles here are subduction-related volcanoes. And there. Okay, this is the East Pacific Rise, which is a mid-ocean ridge. And the way plate tectonics works is that this is one big plate, the Pacific Plate. along the mid-ocean ridge, these two plates are separating from one another. So you're getting seafloor spreading along the mid-ocean ridge and the formation of new oceanic crust as these plates move apart. And then the plate is moving in this direction, and when it gets over here, then it gets subducted, meaning that the oceanic crust slides underneath the crust of the continent over here. And the black are trenches that form on the seaward side of the island arcs. And I'll show you another diagram in a minute that will show you a cross section that I think will help you understand the what subduction is all about. So to understand why you get volcanism and where the volcanoes come from, that's what the next couple slides are about. So keep in mind that when you melt rocks, there is an increase in volume. So the liquid is less dense than the solid, therefore it has a tendency to rise. And the liquid also has gases like water and also carbon dioxide dissolved in it. So as the pressure is lowered, these come out of solution and help drive the liquid up. And the rocks also melt through a range in temperature. So what I've shown here, I don't know if you can see this or not, is this is the range. Here's temperature, here's depth, and this is the range in temperature through which the rocks will melt. In the rim of fire, the volcanoes are explosive because water is involved in their formation, and in Antarctica, the volcanoes form from decompression melting without the involvement of water, and that's what I'm going to explain next, is what that really means. So as you go down, this is important to understand why you get volcanism where you do. As you go down in the earth, it becomes hotter due to gravitational compression, meaning as you increase the pressure, you generate heat. It's like when you pump your bicycle tire up really hard and feel the tire, it's warm. And it's the same principle as gravitational compression in the earth. Radioactive decay is the main thing that generates heat. When the nuclei of uranium, thorium, potassium decay, they emit particles that hit matter and generate heat from their kinetic energy. And that's sort of like hammering a spike into an oak plank and then feeling the top of the spike, and you feel that that's hot. And then there's original heat. Everybody's pretty sure there's original heat from the time the Earth formed and was bombarded by meteorites. There are all sorts of guesses as to how much there is. Nobody really knows. The melting temperature increases with depth because when the rocks melt, they expand. Okay, so this is what the melting temperature looks like. As you go deeper and deeper, you have to heat the rock hotter and hotter because as you melt it, it's expanding, and so it's got to lift all that rock above it. So you need more thermal energy to actually melt it. Okay, then the radioactivity of uranium, thorium, and potassium is what produces most of the heat, and those elements are concentrated in the upper 100 to 200 meters. So if you want to look at this afterward, I've got uranium, potassium, and thorium here. Most of it up here. Here's 100 kilometers down. So it keeps getting, you keep getting less and less. And so I've shown, let's see here. The melting begins at depths of 50 to 250 kilometers where the temperature, so here's what's happening. Here's the melting temperature of rock. Where you've got a lot of uranium, potassium, and thorium, the temperature of the Earth increases relatively quickly until it crosses the melting temperature of the rock and starts to melt it. But the rock melts through a range in temperature. So it doesn't all melt at once like ice does. But when you get below 100 kilometers, so you're running out of the radioactive elements, and so then the heat doesn't increase as rapidly as it does up here. So it crosses the melting temperature curve here and then crosses it again back here. And so in here, you have a zone where there's about 5% melt, and that's in a part of the Earth called the asthenosphere. So there, within the asthenosphere, it's partly molten, but you don't get volcanism where you only have 5% melt. You need something extra to produce volcanism. So that's where this comes in. And this is way out of scale just for illustrative purposes. It's 2,900 kilometers from the surface to the core, and it's only 250 kilometers through the asthenosphere. So this has been expanded so you can see what what they want to show here. So this is the part, the asthenosphere is the part, means weak sphere, that's 5% molten. The upper part, the upper 100 kilometers or so, is the crust and upper part of the mantle, which is completely solid. And that's what forms the plates. That part is what moves around on the asthenosphere, as the arrows are showing. And so where you get convergence, like here, then you get subduction. And so you get the oceanic lithosphere here being subducted or slides underneath this plate here. Now, the thing that makes it work is the lithosphere is water saturated. As it's being subducted, it's squeezing the water out, and water lowers the melting temperature of rock. Water lowers the melting temperature of rock, just like when you put antifreeze in your radiator. So it's being subducted here, squeezing water out, the water rises, and that causes melting, which produces the volcanoes everywhere in the circum-Pacific except for Antarctica. In Antarctica, you get rifting, where this is stretched and breaks the lithosphere here. Now, because the asthenosphere is partly molten, it's less dense than the lithosphere. And so it tends to rise. And when it rises, the pressure obviously goes down. But the temperature does not go down very rapidly because the rock is a very poor conductor of heat. Heat flows very slowly through it, which is why you drink your coffee out of a ceramic mug and not a tin cup like they gave me in the Boy Scouts. So what you have to imagine now is rock is moving from down here where the melting temperature is down here, and as it rises, the melting temperature goes down, but the temperature is staying essentially the same. So as you go like this, more and more of the rock is melting. Okay? That's what's producing the volcanoes in rift zones like Antarctica. Okay? And that's called decompression melting because of the fact that it melts because of the lowering of pressure, but the temperature stays the same while the melting temperature goes down, and that's what produces the volcanism. Okay, there we go. Okay, I've got just a few more slides here about hazards. Yeah. We're in an Adelie penguin rookery. The Adelie penguins are just under knee high, and they have no enemies on land. None of the penguins have enemies on land. Their enemies are killer whales and leopard seals. So all their enemies are in the water, and you can walk through the rookery and work. pay any attention to you, except if you get too close, they'll peck at your boot. But you can work like this. Now, they are awfully cute. And one of my field assistants could not resist picking one up to give it a hug. So he did. And it pooped all over him. So they don't like being hugged. They're not afraid of you, but they don't want to be hugged. The pink that you see is penguin guano. So this is a rookery of Adelie penguins, and there are thousands of them. All those little black dots are Adelie penguins here. And they've all got to get down to the water for food. And, you know, if you've ever seen a penguin walk, they are not fast. So you got to wonder how they get down there. And looks like they ski. You look at this guy over here. When the snow is cold and hard, it's quite slippery. It's just, you know, you like to ski on cold snow. When it starts melting, then you can't ski as fast. And there are these ski trails all over where the birds have skied down to the water to get, but then they have to walk all the way back up here. I've often wondered whether there's some kind of social hierarchy where the ones higher up get to build their nest down next to the water. Okay, this is taken late January. These are the chicks that have now hatched, and they call this the creche stage. They all like to be together, and they are these fuzzy looking things. It takes them so it's 2 months from the time I took that picture with the egg, and the adults are the ones that have the white. And here, these are emperor penguins. They're about waist high. And we saw them way over in here, and I was thinking, gee, I wish we could get over there to see them. Well, we didn't have to. They came over to see us. They're quite curious. And so they came, and you know, they scoot along on their bellies like this, propelling themselves with their feet and steering with their, sorry, I'm taking too long here. But, you know, we could take pictures of with a guy sitting down next to them. They're just not afraid of you at all. And they really wanted to just look us over. And this is, oh, let me see. Yeah, I was going to tell you the penguin picture. The Adelie rookery was over here. The emperors were down here. This one is at Palmer Station, which is way up here. And then this is a minke whale. I did not take this with a telephoto. This is the last slide. I didn't take this with a telephoto. This was down here. We were waiting to get on an icebreaker, which is right over here. And the icebreaker breaks a channel into McMurdo Station, which is the main station here, in about late January so that resupply ships can get in there. And when they break the channel, it's like opening a whole new cafeteria for these whales. And the whales are, their eye is back in here. And so this was porpoising along. I could have jumped on his back, literally. And they do what they call spy hopping. They raise themselves up like this, so their eye is out of the water, and they can look at you. And there were, I don't know how many of these whales that were porpoising all around us and spy hopping to look at us. And so that went on for, you know, an hour or so until we went on board the icebreaker, had a meal, and I thought, I'm going to come out and see whether they're still out there. Well, I had to wait for quite a while before one finally poked his head up. So it was clear they were looking at us, checking us out, and just as curious about us as we were about them. Thank you very much. Any questions?
Yeah, so you said that most of the volcano is basically beneath the ice
Yeah.
sheet. So with the ones, because it has a gentler slope, does it extend wider than
Yeah.
other volcanoes?
As much as you can tell, yeah. I mean, that's based really on one volcano, that one that I showed you that had the deep cirque in it. That's the only one that's exposed from the base of the volcano to the top. And so that, has to be a model of what the structure is like, and it's 90% basalt. And then there are 3 or 4 others where there is a thick section of basalt under the trachyte. And then for the remainder, there are 18 of these volcanoes in the area where I work. And so there are only about 4 or 5 where you can, one of them where you can see the whole structure, and then another 4 where you can see that there's a thick section of basalt, which tells you that it's pretty much like the one that's completely exposed. I mean, there's one volcano that's right here, right on the coast, and it rises from the sea to a little over 3,000 meters, and it's all basalt up to just below the summit. So but you don't know where the base is. The base is down below sea level somewhere. So that again tells you you've got a very thick section of basalt, and when you see the profile of that volcano, it's like the one I showed you of Mount Takahe, where this very gentle shield shape.
How recent have there been eruptions down
Mount Erebus, which is the one over here, is continually, I mean, it's always fuming, and it's throwing out bombs, that is, blocks of lava that are bomb-shaped. They're liquid, and they chill and freeze in the air, so they often have raindrop shapes, they're like this. And it throws these things out periodically. That's the main kind of eruption that it has, and then it'll settle down to more steam. The other ones, like Mount Berlin, that's in there, there is a blanket of ash on the next volcano over. So, and it can be dated. It's only thousands of years old, which geologically is extremely young. And so it's clear that that volcano is active. Mount Takahe, the dates from the lava up around the summit are only a few thousand years old as well. So that's how you know. Nobody has ever been there and seen one erupt. Yes?
Okay, supposedly is it Mauna Kea or Mauna Loa are the tallest mountain in the world? If you
Yeah, you start out
include from the base.
14,000 feet below sea level and end up 14,000 feet above sea level.
Right,
Yeah,
right.
yeah.
So, could any of these volcanoes in Antarctica rival that, or we just don't know where
They're not
started?
that big,
They're not
but
that big.
if you take Mount Takahe and if you say, okay, what's exposed at the surface is 10% of the volcano, and then calculate what the total volume would be with the shape, you just kind of, it would be the size of Kilimanjaro, which is big. Yes?
Everybody wants to climb.
Pardon me?
What mountain is it that people go to Antarctica to climb?
You mean the mountaineers that want to climb the highest
Yeah,
peak
the
in Antarctica? They climb the Vincent Massif, which is over in here, in the Ellsworth Mountains. Vincent Massif is located right here, 16,067 feet above sea level.
Pay the Navy to fly them there?
Do they have what?
Do they have to pay the Navy to fly them there? Or
They fly in and land, like they don't all use Hercs. They've got twin otters that will fly them in from South America You know, they raise money to pay somebody to fly them in.
So they use commercial.
Yeah, yeah. The ones that I was showing you, that's logistics supported by the National Science Foundation, and they don't fly people in to do mountain climbing. It's all, they have occasionally had to rescue ships, you know, like the Lindblad Explorer. The first time or two before they got experienced enough, I think they ran aground and they had to send an icebreaker, which annoys the National Science Foundation and all the scientists because that some guys just didn't get their work done that summer because they had to rescue these people. Yeah.
Two questions. What time of year are you working there?
The
And
awesome.
thinking of your career, the time you spent there, I mean, what's kind of your primary research question? What do you...
Oh, okay. It is, you go down, like in Murray Birdland, the first time I went down, we went down in November, and it was blizzards for a month. The only time we could start working was in December and January. Those are the 2 months where you get relatively stable weather. When you go down, when I went down, the first time was in '67, we knew there were volcanoes. There had been a couple other expeditions over snow traverses that described them as volcanoes. They didn't know what kind of volcanoes they were. They didn't know that it was a rift environment or anything like that. So basically you're going in and developing the problems because you don't know what they are when you go there, and when you get enough information then you know what the problems are. So that's the fun of it, actually. I really enjoyed that. Yes, ma'am.
Is there any earthquake?
Almost none, which has been a puzzle to people. But in more recent years, they've set more seismometers around, so they do get a little bit. And some of it is just what they call ice quakes from the glaciers. But there's really very little earthquake activity there. Yeah, Becky.
I vaguely remember you talking about sometime back when I took your class. About
I'm glad you vaguely remember something. Thank you.
no, about this basalt that's white. And I thought you said it was from Antarctic. It was like a white, it was a basalt that had this, I thought it was basalt that was very unusual, and I forgot, I thought it was some kind of weird chemical.
I thought there are sometimes crusts of gypsum and calcium carbonate on some of them.
Oh, maybe that was.
Yeah, but it's not common. It might have been from the dry valleys where they, you know, there is no ice sheet in the dry valleys. But you're talking way back there,
Yeah.
when I don't remember what all I showed you.
But isn't it true that Antarctica is sort of a desert?
Yeah.
In the sense of
A lot of the now where I worked in Murray Birdland here, they do get I can't remember amounts of snow, but they do get new. But then a lot of it in a blizzard is just blowing the snow around. But there is new snow that you get here. But back in here, there's very little new snow that precipitates. Yes.
Do you or any of your colleagues actually climb Mount Erebus, or is it just too active?
Oh no, guys go up there all the time to study it. There's an active lava lake at the summit, and there are a lot of these fumarolic ice towers around. So they, and I know the guys that do it, and they were going to take me up there. We're all set to fly me up there. And the guys at NSF said, you don't have this in your proposal. We can't take you up there. So I can't show you any pictures of the summit of Mount Erebus. Yes?
Well, it seems to me, on the face of it, a little odd that there would be glaciers below sea level.
Well, no, when they come down, no, once they get to the sea, they will flow out and they will be, they will flow out until they are in deep enough water that it floats the ice and forms an ice shelf. So that's what you get.
You were talking about the diagram of the volcanoes.
Yep.
The glaciers below sea level. The glaciers started below sea level.
Yeah, that's right. And the glacier, yes, those ones in here are grounded below sea level.
Yeah.
That's right. Well, they are thick enough that, they are not, you can't float it on ice when it becomes thick enough. That is, the thicker it gets, the deeper it sinks in water. And when you get it thick enough, then it will rest right on the bedrock, even when it's well below sea level, which it is here. And there are some of those where I showed that diagram with those little blue troughs. One of them gets down 2,500 meters below sea level. That's almost the depth of mid-ocean ridges, and it's filled with ice. So the ice is thick enough that it doesn't float. But what's worrisome is that as it flows out to sea, as this accelerates, and it seems to be accelerating, it will eventually get to a point where it will thin the ice in here to the point where it actually will dislodge itself from the base and start floating. But it depends, it's a matter of the thickness of the ice. And it will flow out to sea until it is in deep enough water to float it. Does that make sense? Anything else?
Well, if there's no more questions, let's
I
take
want
this
to
one.
Yeah.
So you've done all this work and it seems to be great, but the bottom line is, what are we gaining out of this? Are these helping us to identify, like you say, and there's a lot of concerns that some of the things are melted, right?
Yeah.
Do we consider that global warming is causing it, or is this a natural progress of how the Earth is created?
It's a combination of things. I mean, all through geologic history, there have been fluctuations in temperature, and there have been times when Antarctica, especially West Antarctica, has been completely deglaciated, and then it's come back again. But now, the rate of temperature rise is greater than anything we have a record for in the past. And what is happening is the melting is taking, and for these glaciers that are down, that are here, they are melting from underneath because the seawater is warm enough to melt those. So there's more melting from underneath than there is at the surface. And that's worrisome because as the water moves back under, it's going to, there's a chance of, so, so what else is useful? Now, that's not what I work on. What I work on is fun for me, but it's not going to be a cure for cancer. It's one of these things like there are people that are interested in volcanoes and in Antarctica and things like that. And, the overall picture that I get from this, I've talked to you about the melting in the mantle. Well, then what happens is as that melt rises, I mean, it doesn't all immediately rise to the surface. It will stop different places, and where it stops, it'll start to crystallize. And when it crystallizes, then it will change the composition of the liquid that remains. So you end up with a whole variety. Trachyte's just one example. It starts out as basalt, but it's like a huge distillation column, like you're forming brandy from champagne or something like that. But you're distilling it from 100 kilometers or more, and it's over an area of 500 to 800 kilometers. All of that is being distilled, and that lava keeps rising from it and has been doing that probably really for the last 34 million years. So it's, to me, it's a very fascinating glimpse of what's going on in the Earth.
And to add to that, if I understood right, at one time or another, we didn't know there were volcanoes in Antarctica, right? And if so, when did we actually establish that they were?
Well, I know that the guys that went down there in the 50s, when Byrd went down, see, in this, they've known about Mount Erebus from probably the 1800s, which is when they first, and then, you know, Scott and Shackleton were there around Mount Erebus in the early 1900s. So they knew that was a volcano. In here, these were first, you know, described as volcanoes probably in the 50s. That's my, when I think about, you know, where the stuff that I've read. But one of the other amusing things, every now and again, I have been asked, how can there be volcanoes in Antarctica when it's so cold? I figured you guys are more educated than us, so I did not bring that up. I didn't think I had to explain that to you.
So where's the mountain that was named after you?
The garden spot of the Rupert Coast. Yeah, right. It's right in here, right in there. Yes.
Besides the continent is this big, how much of that would be above sea level if the ice weren't there?
Almost all of this, and just this bit here, and a little bit in here. There are a few places here that are below sea level, but and there are places where there are big lakes underneath the ice. But for the most part, all of this, you know, is a craton like the Canadian Shield and the mid-continent of the United States. Yes?
Do you see much plant life, probably just along the edges of
You know, we've, in one or two of the seasons I was down there, we had biologists that got all excited when he found a lichen on a cobble in here. When you get up in here, you get mosses and lichens. But when you're down here, you get essentially nothing except right on the coast you might get some lichens, but they're not common at all. Yeah.
So is it really rock or is there soil?
It's pretty much rock. You get places where the rock has been broken up by freezing and thawing, but you don't get you know, chemical changes in the rock that you would get in a soil here.
More questions? Let's thank once again.
Thank you.